Okay, so today we're going to talk about the combination of vibration and rotation. So we have a molecule that is rotating like this. So let's do CO2. So my head is the carbon, my hands are the oxygens. So it's rotating like this, and it's also vibrating. So it's doing this, vibration and rotation at the same time. And so there's a vibrational quantum number and there's a rotational quantum number. And both of those can change. And if it was an electronic state, the electronic quantum number could change too. So think about how complicated the transition dipole moment integral would be. We would have an electronic wave function and a vibrational wave function and a rotational wave function, and then light in the middle, X, Y, or Z, and then the rotation, vibration, and electronic wave functions again. So that integral would be ridiculous because it would have all of those wave functions multiplied by each other. So there's a large chance that we would have transitions allowed both rotationally and vibrationally at the same time. And so that's what we have in Rovibrational spectroscopy. We're not doing electronic changes, but in iodine we will. So in iodine we'll have an electronic change and a vibrational change and a rotational change. The thing that makes our spectrum a little bit simpler in the iodine lab is we're just not able to resolve the rotational changes. So the rotational lines are there, but we just can't see the individual transitions. So all we assign then is just the vibrational changes. So here's the harmonic oscillator potential. We have the vibrational energy levels there. And then we have these red lines here. Those are the rotational energy levels. So let's zoom in on this bottom area here. So this is a combined spectroscopy of rotation and vibration. And so we just combine the words rho vibration. So whenever you see that rho in front, you know that we're talking about both rotation and vibration. So if we zoom in here, we're going to be looking at both of those energy levels. Now notice here, this is just a convention that got started when they first did these experiments. They were using emission spectroscopy. And so the initial state was the prime state, and the second state that it was going to was the double prime, because that's typically the order of things, right? If I'm going to put a prime on something, I'm going to put a double prime on the second thing. And emission, that makes sense. You're starting in an excited state and you're emitting to a lower state, and so prime was the upper and lower prime was the lower. So we just kept that. So now we're doing absorption spectroscopy in our lab, but still we keep that double prime as the lower state, just to be consistent with the literature. Okay, so that's why we have this this odd set of labels on our quantum states. Okay, and the single prime is the upper state. So let's look at a single beam spectrum of air and see what we see just in air. So if we just have our hot source, our glowing ceramic resistor, sending infrared light through our spectrometer, the air in the spectrometer will absorb some of that light, and it hits our detector, and we get this. You know, this curve is very similar to a black body curve. The overall profile looks like Planck's law. I mean, the Planck distribution. And the maximum here would be, you know, would change with temperature. And so that's the overall shape of a single beam infrared source. And we could find that maximum, sort of model a curve to that, and we could determine what temperature our source was at. But what we want to look at is what these absorptions are. So we've got this black body curve, and yet we see certain things that are stealing light. Like the overall curve is the light of the source, infrared energy coming off the source. But what are these little sharp lines? They're dips. Because there's a molecule in there and it's absorbing some of that light. So it's stealing some of the light so the detector sees this drop. Well, over here on the left side, the high energy side, those are the bond stretching regions. And they're bond stretching, they're high frequency because the spring constant, K, is pretty high for bond stretches. You're pulling these this bond apart and stretching it out when the electron cloud wants it to be closer. Okay, you may say, but the nuclei are charged positive, and that's true. They want to repel each other, but the electron cloud is pulling them together. And so there's this balance that gives you the equilibrium bond length. So if you stretch that bond or compress it, it's going to go up in energy pretty fast because of the force constant. Then there's the angle bending. It doesn't take much to bend a spring. And so since you're not really separating the nuclei very far when you bend molecules, it's really like if this is water, those two hydrogens coming together, there's not much of a restoring force until those hydrogens get really close. And then there's some repulsion and it pushes it back. Okay. So it's very easy to bend a molecule, a very small force constant, K. And so those are the lower frequency values. So let's look here. This is the CO2 vibrations. So this one here is the stretching, CO2 stretch. That's the asymmetric stretch, actually. So it's doing this, stretching. And then this is the CO2 bend. So if my head's the carbon and these are the oxygens, this is the bend, right? See the molecules bending. Okay. And then we have the same thing with water. So over here, those are the water stretches, the OH stretches. And then here's the bending of the molecule, water. So changing that angle. And then here's some little bitty peaks right here. And that's just the residue, fingerprint residue on the windows, the optics of the spectrometer. And, that's sort of, taking responsibility for maybe having a smudge or a fingerprint on there, but it's also the forest in Huntsville. So these trees are just spitting out pinings and organic molecules. And so they're everywhere. And so if they're everywhere, they're going to land on our optics. And so just being in a forest that's spitting out all of these organic molecules that are going to land on our windows over time, and we'll get some residue. So let's look at this. This is the bending of the CO2, and it has these different sets of lines, which we've labeled with some labels. You see all of these little rotational lines. These little bumps are real. So that series of bumps, those are rotational lines, and that's the R branch. Over here, this is rotational lines in CO2. This is the P branch, and we're going to learn what this P, Q, and R branch means today, because those apply to Rovibrational spectroscopy. If we zoom in on the stretching band, we don't see a Q branch. We just see a P branch and an R branch, and we see that the lines are stronger here. So we see that we can really resolve those rotational bands. So we have the P branch and the R branch. Now I called this a perpendicular band over here. This other one's called a parallel band, and it's because the vibration is either perpendicular or parallel to the principal symmetry axis. So this is a linear molecule. So the z-axis is the axis of the molecule, and if it's stretching along that z-axis, that's a parallel band. If the stretch is going 90 degrees to that, it's perpendicular to the symmetry axis. So let's look at this motion, and we'll look at the spectral lines and understand this P, Q, and R branch business. So here's a vibrational and harmonic vibrational potential. We can see here molecules vibrating, lots of energy levels. This happens to be showing the one in the third energy level, but we're going to zoom in here on the 0 and the 1. So if we zoom in here, we get this energy level diagram. And so the energy level diagram is going to follow these rotational lines and the ground vibrational state. So we have here the ground vibrational state, V double prime equals 0, and then J double prime 0, 1, 2, and 3. There's hundreds of rotational lines, but I can't show all of them on the screen. So I'm just going to show the lowest 4 rotational lines. So we have 0, 0. So V double prime equals 0, J equals 0. So that is the ground state. Then we have the first excited state in rotation. Still the ground state vibration, but first rotational excited state. Then the second, and then the third. So we have those 3 or 4 energy levels in rotation, ground state plus 3 excited states. Then we go up to the upper vibrational state. So the vibrational quantum number, V plus a half, times the vibrational frequency. That's where we would plot V prime equals 1. So this is the upper state, V prime equals 1. And then there's the J prime, so 0, 1, 2, and 3. So we have 4 rotational lines shown on the first excited vibrational state. And everybody, can you see that that's just this little box right here? Okay. At this temperature, all of our molecules are in the ground vibrational state, but these rotational states are close enough that we have thermal excitation. So we do have hot bands. We have molecules in the rotational levels that are excited, but we don't have any vibrational hot bands. We have rotational hot bands. And so let's look at those. We can have transitions. If we look at our selection rules, V plus or minus 1, so we can go from 0 to 1. That's allowed. And then the delta J's can be 3 options. So we can have a 0, a plus 1, or a minus 1 in J. Okay. So pay very careful attention. It took me a long time to make this slide because I had to be very picky about where my arrows begin and end. So that's the purpose of this exercise, is for you to look in this region, the beginning and ending of the arrows. So we're doing absorption. So if delta J is 0, we can go from 0 to 0. So the delta J is the delta, like upper minus lower, right? So we're going from 0 to 0. So that's delta J equals 0. And then here's 1 to 1. That's also a delta J equals 0. From 1 to 1 in the rotational. 2 to 2 and 3 to 3. So all of those arrows are the same length. That's why they're the same color. And that's what we would call a Q branch. You'll see that in a minute. But that's going to be the very center. That Q branch is right at the vibrational difference. You can see because V is going from 0 to 1, and all of those energy levels have the same spacing pattern in the ground state and the excited vibrational state. And so this arrow is the same length as that one. It's going 0 to 0. This is going 1 to 1. It's going 2 to 2. So it's just like I've moved that arrow up, and it's the same spacing all the way up. So whenever we look at the absorption spectrum, all of those arrows show up right on the same spot. And we saw that with the carbon dioxide spectrum. That Q branch was huge because it was a bunch of rotational transitions all on the same frequency. Okay, let's look at the delta J plus 1. So this is going from 0 to 1. You see up there, it's 1. So, the final minus initial, we have 1 minus 0. So that's, again, delta J plus 1. This next one goes from 1 to 2. See, so it's going from initial state 1 to final state 2. So that's a delta J plus 1. And then this one is going from 2 to 3. I can't show the 3 to 4 because I don't have 4 drawn up there, but it exists as well. The longer the arrow, the higher the frequency. So notice down here, frequency and wave number are proportional to each other. And so these are going to be spaced out to the right. This one, the 2 to 3, is a longer arrow than the 1 to 2, and that's a longer arrow than the 0 to 1. So these would give us 3 equally spaced spectral lines, and that's going to be called the R branch. Okay, what about this? We could do a delta J minus 1. Well, it's final minus initial, so I can't go from I can't hit I can't go from 0 to minus 1 because there are no negative quantum states. Okay, so I have to start this one in level 1. So this was going 1, and it's going delta J minus 1, so it's going down to 0. So 1 to 0 is this yellow line. What do you think the next one is? It's going to be 2 to 1. So that one is going from state 2 to state 1. Notice how these levels, the spacing goes up as J squared, right? The energy equation is B times J plus 1. So there's a J squared term in there. So as I go up in quantum number, the spacing jumps up by the square, just like the particle in a box did. And so this second energy level jumps up quite a bit from the first, but I'm only going to the first up here. So this gap right here causes the orange arrow to be much smaller than the yellow arrow. And then the same thing happens when I go to 3 to 2. this gap right here causes this arrow to be even smaller than the orange arrow. So those arrows get closer and closer together, or smaller and smaller, and so they're going to be at lower and lower frequencies. So when I look at the spectrum, the P branch goes towards lower wave number, and it ends up being equally spaced. We'll prove that in a minute. So this is what we see in the spectrum. This is the spectral lines. This is the horizontal axis of the spectrum. Notice the selection rules gives us our transition equation, and those differences between those energy levels gives us our spectral lines. So this is what we would see in the spectrum, and we could assign quantum numbers to all of these and get physical properties of the molecule out. Any questions before we move on? These are labeled the P branch, the Q branch, and the R branch, and it's just alphabetical in increasing wave number. So P is the lowest wave number 1, Q is in the middle, and then R is the high wave number 1. So that's where the PQR comes from, it's just a labeling system. In increasing wave number, PQR. If you can have this in your mind when you're looking at Rovibrational spectroscopy, then it'll make sense. If you kind of zone out on this, then you're going to be looking at a bunch of spectral lines and it's not going to matter to you. You're not going to connect with it. This is the key right here to everything. Because if you can understand the energy level diagram, then you can understand the spectral lines. So that's the goal of the course. Right there. This is to teach you about quantum mechanics and spectroscopy. It's all right here. Quantum mechanics gives us the energy levels, and the spectroscopy interacts with it and gives us our spectrum. So if you can understand the energy level diagram, you can understand what's going on at every one of these peaks that you get in your experimental data. So this energy is the sum of the vibration or rotational energy equations. So these are the energy equations. You see that we've got the energy for vibration and the energy for rotation. So here's the vibrational energy, here's the rotational energy. And so we're not counting anharmonicity, which would add in a V squared term and a V cubed term, or centrifugal distortion, which would subtract some energy away from the rotation. As the molecule spins faster and faster, it tends to stretch. So think about a centrifuge, right? As it spins faster, there's pressure on it. So as this molecule, here I'm a CO2 again, as I spin faster and faster, the bond starts to stretch. And then that tends to slow the rotation down. So just like a figure skater, when they stick their arms out, they slow down. When they pull them in, they go faster. Same thing for molecules. So as we go up in quantum number, faster and faster, we start to stretch the molecule a little bit. And we can actually determine that by looking at the spectra, and you'll do that for carbon monoxide. So let's look at the combined selection rules, plus or minus 1 for vibration, and the rotation 0 plus or minus 1. And so here are the transition equations. So for the P branch, we put in, and I would love for you guys to do this on your own, so verify these. So what we did was we put in V plus 1 and J minus 1, because that's what the P branch is. We're going up in vibrational state, but down in rotational state, minus the energy equation without making those changes. So wherever there's a V right here, we would put a V plus 1. And wherever there's a J, we'd put in J minus 1 and J minus 1. And then we subtract those same energy terms without making those changes. And then you just do the algebra, and this is what you get out. You get the vibrational energy difference minus 2B times the quantum number J. And then for the Q branch, delta J is 0, so we don't have any changes to the J's, and so when we do the subtraction, all of the rotational pieces disappear. We just have the vibrational energy difference. So it's just the vibrational frequency. So that Q branch falls right on the vibrational difference. And then the R branch, we would put J plus 1 in for all the J's and V plus 1 for the V, and then subtract those without those changes and get this equation. So we get the vibrational difference plus 2B, and this is I've written it a little different than what you have in your notes. I went ahead and pulled 2B out, so I'd have a J plus 1. So we can see that that P branch is J and the R branch is J plus 1, and we'll see how that figures in later. But the spacing, the slope with respect to our quantum number, our rotational quantum number, is 2B. So every one of those spectral lines will be separated by twice the rotational constant. So here's our Q branch and our R branch and our P branch. And so that 0 to 1 line, so if we put 0 in here, in for J, because that's that spectral line, it's labeled with the J equals 0, then this is the vibrational frequency. So this one is the vibrational frequency plus 2B. So it's 2B away from the vibrational frequency, because I had 0 plus 1, so 1 unit of 2B. What if I go to the next line? It starts at 1 and goes to 2. So if I have a 1 here, then it's 1 plus 1, so that's 2. 2 times 2, that's 4, so 4B spacing. So this is going to be further up on the spectrum from the 0 to 1 line by another unit of 2B. It's going to be 4 away from the Q branch. What about this one, the 2 to 3? So if I put a 2 in here, 2 plus 1 is 3. 3 times 2 is 6. So it's going to be 6 away from the vibrational frequency. Well, that's 3 units of 2B. So that's going to be another 2B away from the previous line. So you can see every one of those spectral lines is separated by 2 units of the rotational constant. What is the rotational constant again? We'll see it later, but it has the mass of the molecule and the bond length in it. So the properties of the molecule are in B. So if we can find B out of our spectrum, then we can find the bond lengths and masses of our particles. Let's do the P branch now. So if we put in here, the P branch has to start at 1 because it's going down, and I can't go to negative quantum numbers. They don't exist. So the P branch has to start in the first excited state down here and go from 1 to 0. So 1 to 0. So we label this bottom one. These spectral peaks are labeled with the bottom quantum number. And so this is 1. So 1 unit of 2B subtracted from the vibrational frequency. So that's negative 2B away from the vibrational frequency. If I put a 2 here, so now this is a 2. 2 times 2 is 4. So this is 4 units of B away from the vibrational frequency. And then if I put a 3 in there, then it's 6 units away. So you see every one of those spectral lines goes down in wave number by a factor of 2B. Okay, that's what we're going to be doing in lab. We could, if we had a higher resolution Raman spectrometer, we could do Raman Rovibrational spectroscopy. We're not doing it in lab, but let's go ahead and look at the Raman spectral lines and see what we get. So, same energy level diagram, but a different experiment, which means we have different selection rules. So in this case, we have the Raman effect, where we go up, we oscillate with a visible photon, this green laser, and then it spits out a red shifted photon because of the vibrational difference, but we could also have all of those rotational differences too. So here's our Raman selection rules, and we'll actually be plotting this with what we call Raman shift. Raman shift, which means we've already subtracted the incident laser wavelength. Okay, and so we have the Q branch with delta J equals 0, so those will be showing up in the middle. And then let's look at this one. We could have a delta J of plus 2, so this one's going from 0 down here to 2 up here. So 2 minus 0 is 2. The next one's going from 1 to 3. So again, 3 minus 1 is 2. So this is, again, starting down here at 1 and going up to 3. That's the only one I can show because I don't have 4 plotted. But there's 4, there's 2 to 4 and 3 to 5 and so on. So these would be showing up in these spectral lines. let's do the delta J minus 2. So if I'm going to go minus 2 and I can't go negative, this one has to start at the lower J value of 2 so it can go down to 0. I can't start at 1 because I'd have to go to minus 1 and there are no negative quantum numbers. So this is what we have. And the next one goes from 3 down to 1. You see, those arrows are much shorter. Just look at the lengths of the arrows. The blue ones are the longest, and the red and the orange are the shortest. And I did that on purpose, right? When you know the blue light is the short wavelength side, high energy light, and red is the lowest energy light. So here's our orange and our red transitions. So this would be a rotational vibrational Raman spectrum. And in this case, those are going to be further down because they're delta J minus 2. They're going to be further down from the P branch. And so keeping our alphabetical scheme, that would be called an O branch. And in the middle is still the Q branch because it's delta J 0, just like in the absorptions experiment. And then what do you think the top one is called? It's the S. So we have O, P, Q, R, S. But O and S are Raman, and the P and R are absorption. So we would never see those in exactly the same experiment, but we could overlay them. But we would have Raman give us the O, Q, and S, and then regular absorption, FTIR, would give us the P, Q, and R. So let's look at the transition equations in Raman shift. Same kind of thing. We have our overall energy equation, our selection rules. We could take this Raman shift, which is the incident minus the scattered light. And so we're looking at that difference, and that's going to be proportional to our vibrational frequency. So we have this vibrational difference, the vibrational frequency minus, and I've written this a little differently than what you have in the notes. I went ahead and pulled 4B out. And so I have minus 4B, J minus a half for the O branch. For the Q branch, again, delta J is 0, so all of the J differences cancel, and there's just a vibrational frequency. And then the S branch, I pulled 4B out, and so we have J plus 3 halves for the S branch. So this gives us our spectrum up here, the Q branch, S branch, and O branch. So the Q branch is right there at the vibrational frequency difference. And then let's put in for the S branch, it's 0 to 2. So we're going to start at 0. So we have 0 plus 3 halves. So 3 halves times 4. Well, 3 halves times 4. Let's just take that 4 and multiply by the half. So we end up with 2. 2 times 3 is 6. So this should be 6B above or higher wave number from the vibrational line. So 6B spacing. Now let's go the J1 to 3 transition. So we would label this with quantum number 1, J equals 1. So 1 plus 3 halves. Let's make this 1. Let's call that 2 halves. Is everybody comfortable with that? 2 halves is the same as 1. So 2 halves and 3 halves, that gives us 5 halves. Okay. 5 halves times 4. Let's take the halves and the 4 and make 2 out of it. So 2 times 5 is 10. So 10 units of B away from the vibrational frequency. So that's going to be 10 units away, or 4 away from the previous line. So the Raman spacing is 4 times the rotational constant. And that was the point we wanted to see. And you can see this here in both of these transition equations. The Raman spectral lines, if we just look at the slope of J, is 4B. Every spectral line is 4B away. That's good to know, because if we get a Raman rotational spectrum, we take the difference in those lines, divide by 4, and we have the rotational constant. And we can use that to calculate bond lengths and masses and stuff like that. Let's do the P branch. So here we have starting from 2. So we have a 2 here. 2 minus a half, okay, is a half, okay. So half of that, okay, 2 minus, okay, so let's do this. So 2 halves, that would be 2, that would be 4 halves minus 1 half, so that's 3 halves. So 3 halves times 4, the half and the 4 gives us 2. So 2 times 3 is 6, so negative 6B. So it would be 6B away from the vibrational frequency. let's do 3 to 1. And so now we put a 3 in here. All right, so that's going to be the same as 6 halves minus 1. So we're down to 5 halves times 4. So that's going to be 10. It's going to be a negative 10 units of B away from the vibrational frequency. So this one is also separated by 4B. And we can see that that is the slope of this negative 4B is the slope with respect to J. So every one of those spectral lines will be 4 units of the rotational constant. So we have this situation where Hamlet's wondering, to be or not to be? That's the question. You've heard Shakespeare, yes? So if it's the absorption spectrum or the Raman spectrum, it depends, right? So my answer is, if it's absorption, the answer is 2B. And if it's Raman, it's 4B. Okay, it's one of my favorite jokes. Okay, so thank you for at least smiling. All right. So it's important because there's no units associated with that 2 or that 4. So if you don't know what experiment you're getting the rotational lines from, then you're not going to be able to know what to divide by. So unit cancellation, which is the key to 95% of our chemistry problems, is following the units. This is an example where units won't help us. You got to actually know what experiment you're doing. So in your carbon monoxide spectrum, it's a straight absorption spectrum. This is what you will get. And so you see those rotational lines, and since you know it's a direct absorption spectrum, you know that those lines are separated by twice the rotational constant. So if we look at this spectrum, over here on the left is the lower frequency side, that's the higher frequency side, so that's the P, Q, and R branch. But diatomics can't have a Q branch. All of the vibration in a diatomic has to be along the symmetry axis because there's only one bond. And perpendicular bands don't have Q branches. Okay. What I haven't really talked about that, but let's look at the Q branch. What's going on with this Q branch here? Notice that delta J is 0 for the Q branch. So what's happening to the rotation of the angular momentum of light? If it's a parallel band, okay, we can't do anything with the angular momentum of light. So we can't have a delta J equals 0. We've got to have some change in angular momentum if we're going to absorb light rotationally. So that Q branch, the light just can't be absorbed because we can't do anything with that angular momentum. Now we also proved that with the symmetry in that paper that Victoria and I wrote. But for a perpendicular band, so like that CO2, let's see, how can I describe this? So let me draw. Put an oxygen atom at the tips of my fingers, okay? And put the carbon atom at my wrist, and put the other oxygen atom down here on my arm. So can everybody see the CO2 right here? So oxygen, carbon, oxygen, okay? And so it can bend like this, okay? That's a perpendicular band. Symmetry axis is going up, so this is a perpendicular band. Well, it could also go like this. Okay, turn it 90 degrees, it could go like that. Okay, so we have an X or a Y bend in that molecule. What if I combine X, then Y, then minus X, then minus Y? I get what looks like rotation. Look at the carbon. It's rotating around the symmetry axis. So perpendicular bands can have a pseudo rotation in the vibration. That's not actually rotating. It's vibrating. But it's vibrating in X and then Y and then minus X and then positive Y. So that pseudo rotation in a molecule that has more than 2 atoms, like CO2, can allow a Q branch. Okay. Because we're not changing the rotation of the molecule, but we are getting that angular momentum in that vibration. So if we increase that vibration, we increase the angular momentum, so light can absorb that without changing the end over end rotational quantum number. So that's why there's a Q branch in perpendicular bands, but not in parallel bands. So in our carbon monoxide spectrum, we only have 2 atoms. There's no way for it to have a perpendicular band, so it has no Q branch, and so we just have P and R branches. And the R branch is always on the high wave number side, okay? So if you plot the data the way it should be plotted with the high wave number side to the left, then the P branch is on the right and the R branch is on the left. So you always got to look at the x-axis. Where are the bigger numbers? The bigger numbers are always the the R branch. The R branch are always the higher wave number values. Okay, so let's do a sample calculation. Once we solve for this rotational constant, we're going to want the bond length. And so you can see the bond length is buried down in the bottom of that. And here's the calculation using all of those NIST variables with all of their significant figures. So it's crazy. We've got Planck's constant, and that's got 8 significant figures. We've got Avogadro's constant, 8 significant figures. We've got the speed of light, that's got, let's see, that's 9 significant figures, okay? And none of those things are going to change. They're constants. Pi doesn't change. You know, the conversion from angstroms to meters and grams to kilograms and all of that. So all of that stuff, this portion of the problem doesn't change. So just consolidate all that mess into one constant, but keep all your significant figures, okay? So this is note card bait, my friends, right? And also useful in Excel. You can have a constant. You don't have to worry about times 10 to the everywhere. So get rid of all the times 10 to this and make a single constant. There's a very nice constant, 16.8576314. You know, but look at the units too. It's in the units I want to use. Like I want to make my reduced masses off the periodic table in grams per mole. I don't want to have to convert everything to kilograms and have times 10 to the 31 or whatever. Okay, so this is a nice little trick. And that way I can just easily get from rotational constant to bond length and back. So when doing this, it's important to use all those significant figures you find in the literature so that you don't introduce error. So your rounding errors can come and bite you if you do that. Yes?
Where does Avogadro's number come from? It's not in the equation up there.
Oh, because I wanted to get the grams per mole off the periodic table.
Gotcha.
Yeah, okay. So I would, that way I don't have to convert to kilograms or anything. So if I was to convert all of those to kilograms or grams for a single atom, I would have to divide by Avogadro's number. So in order to use right off the periodic table the grams per mole, then I have to throw in Avogadro's number. Good question. So here's an example. So the S branch lines in a Raman spectrum for fluorine gas, they're 3.56 wave numbers apart. What's the bond length of fluorine? Okay, so I can look at that. I can see fluorine atom is 19 grams per mole, so 2 of those, 38. The reduced mass is 9.5 grams per mole. We'll calculate that in a second. Here's our constant. Notice I want to get the bond length here, so I need to swap that with the rotational constant. And I also notice that this is a Raman spectrum. This is the thing that I'm telling you. This right here is the spectral lines are that far apart, so I need to divide this by 4 to get to the rotational constant. So here's the rotational constant. See what I've done? I've taken the square root of everything, okay, to get rid of that square, and I've swapped B, E, and RE. And so here's our mass divided by 2 for the homonuclear diatomic, okay. And here we end up with all of these. So this is the piece right here that we've been emphasizing today so much, because if I've got a Rovibrational spectrum and it's Raman, I have to divide that by 4. Notice there's no unit that has to cancel on that. So you would just be totally off if you didn't know about Raman spectroscopy or IR spectroscopy. So 1.41 angstroms, so that's great. Now here's some help for your carbon monoxide lab. So last couple of times we talked about vibrational spectroscopy, and that was helping you for your benzene, chlorobenzene lab, which is coming up. Is that this week or next week? Are y'all doing that now? Next week, okay. So then in a couple of weeks is the carbon monoxide lab, and that's when you get these rotational lines and assign them. So you're going to have this spectrum given to you, and you got to be able to assign the spectrum. So you got to find the P and R branches. So the P branch is on the low wave number side, the R branch is on the high wave number side, and then you zoom in, and that very first P branch line is P1, not P0, because the P branch means it's going down in delta J, so it has to start at 1 and go down to 0 when it absorbs. Okay. And then the next one is the one on the other side of missing Q branches, the R0. Since it's delta J plus 1, it can start in 0 and go to 1 as it absorbs. Okay. And so then once you start there, then you can label all of them. The next one is P2, P3, P4, and all the way down. And you go as far as you can go. I just show P25 on the screen, but there's another peak that's still small, but you can see it. So go to 26, 27, 28. Go as far as you can go. Okay. Those higher values are really important for the centrifugal distortion constant. Then from R0, we have R1, R2, R3, R4, all the way down. And this one's really hard. It starts to run into the CO2 spectrum. So CO2 is coming in here, and it gets real difficult to figure out which peak is related to carbon monoxide. So if you pick the wrong one, there'll be a plot. You can see in your lab handout how to plot to see if you picked a wrong peak or not. Now, if we were to analyze this data for the P branch, we'd get a value for B and some other values too, alpha E and D, E. And if we did a separate regression for the R branch, we'd get different values for those. They'd be close, but what do you do when you get two answers? How do you know which one's right? So it would be better if we could do a single analysis of the whole spectrum, not just an analysis of the P branch and the R branch, but the whole spectrum. So we can do this if we will make up a new quantum number, like I said, a fake quantum number, M, and we need to define what M is. So for the P branch, we're going to say M is equal to minus J. And for the R branch, we're going to say M is equal to J plus 1. So notice for R0, it's M equals 1. Let me zoom in on that. So there's I'm going to zoom in here, and you can see for the R0, M is J plus 1, so it's 1. And then for R1, it's 2. R2, it's 3. And then for P, the P branch, it's equal to minus J. So P1, it's minus 1. P2, it's minus 2. For P3, it's minus 3. And that puts 0 right here at the vibrational frequency difference. So if we do a regression with respect to M, when M crosses 0, we're going to get our vibrational energy difference. So last two slides. So this is the handout that you're going to be reading. This Nibbler lab is from this book. Nibbler is the author. And he suggests using this equation relative to M using a polynomial in M squared, M cubed. But I did some algebra on this because we don't care about M. We want alpha E, we want DE, we want BE. And so don't use the Nibbler equation, use mine. Use this one. Do a little algebra, and then you get those constants by themselves. And then you make columns of those constants. So this is going to be the columns in Excel. Once you assign all the quantum numbers, and again, this is in a couple of weeks, so come back to this video and look at it. Assign those quantum numbers and then create these three columns, a column of 2m, a column of 2m, minus 2m minus m squared, etc. And then when you do the regression, it will produce this output. Okay, this is the output for HCl. I didn't want to do your lab for you, where you could just type those numbers in. Okay, but this is what you get for hydrogen chloride gas. And you'll get an intercept, you'll get an x variable 1, x variable 2, x variable 3. And that's V0, BE, alpha E, and DE. So these are the constants, the physical constants you get after you analyze the data. It's amazing if you look at it. This is our vibrational frequency, and look where our uncertainty is. So it's down in the thousandths place. So we have 1, 2, 3, 4, 5, 6, 7 significant figures on the vibrational frequency. That's very precise. So that's fantastic. If you'll indulge me one more minute, it says down here, use the standard error columns to produce 95% confidence intervals. Okay, so let me just do that real quick. This is the standard error column. And so I would write this, nu 0 is equal to 2885.887, I'd say 887 plus or minus Z times 0.0045. And so what is Z? For 95% confidence, it's 1.96. Okay. And so that's how you're calculating your 95% confidence intervals. We've analyzed so much data, we're going to assume this is a population instead of a sample. And so we're going to use the population Z value multiplied by our uncertainty. So it's plus or minus ZS. There's no square root of n in there. That would be what you did if you had a sample. And so all of your 95% confidence intervals are going to be using Z times S. So Z times the standard error column, that's the plus or minus piece. And then this will tell you where to round. Notice it told me roughly where to round. If I do this 1.96, it's going to double that. It's going to put a 9 here in that column. So it'll be 28885.887 plus or minus 0.009. Okay, and that would be my 95% confidence interval. And then go through the propagation of uncertainty to learn how to do propagation of uncertainty for this lab. So there's a video of that on Blackboard too. Okay, so I'll see you next time.